Hi, this is Peter with CalcBook, and today we're going to be looking at concrete shear wall design. So let's do a little background on shear walls. They are designed to resist lateral loading due to earthquake and wind, which means they must have enough strength to resist shear loads as well as combined flexure and axial loads. And typically, in building design with shear walls, we like to have those walls also supporting gravity loads, which helps resist the overturning forces. And we obviously need to satisfy the requirements in ACI 318, which checks for axial, moment, and shear, and then also the combined effects of axial and moment. So if we look at figure 11413 from ACI 318, it's a good diagram of the forces that you would find on a typical wall. So we have our in-plane shear, right, which is just going to be the lateral force that's transmitted from the diaphragm into this wall. We have the in-plane moment, right, which is going to be that shear, times the height of the wall for that overturning. Then we have the axial force, which is any loading coming from the roof or the floors above. And then we have the self weight of the wall. And we have two other forces there, right? Out of plane shear and out of plane moment. That's not going to be a check that we're going to be looking at today. That's a separate calculation that you'd be looking for either earthquake loads, in the orthogonal direction. But that's not going to be something that we're looking at today. So we will not be reviewing those as part of this. So let's go ahead and look at our problem statement. We're going to be checking this wall in accordance with ACI 318.19. We've got an F prime C of 4,000 PSI. We're going to be using normal weight concrete. We've got an FY of 60,000 PSI for the reinforcement. Our wall is 10 inches thick. We've got number fives at 18 inches vertical, and that's two layers, so that's each face. And then we have number fours at 16 inches on center, horizontals, and that's also two layers, so each face. The loading is as shown in the diagram to the right there, and we've resolved all of the forces at the base of the wall. So we've got an applied dead load of 230 kips. That does not include the self weight of the wall. We've got a live load of 115 kips. We've got a shear due to wind at 121 kips, and then a moment due to wind at 4,670 kip feet. The wall is 12 feet high, and it's an 18-foot long shear wall. So the goal for today is going to be checking if this wall is sufficient to resist the loading shown. So let's go ahead and open up CalcBook, and we'll start the design. All right, we've got CalcBook open now, so let's go ahead and click into our concrete design module. We're going to be going into our standalone designs and then selecting shear wall, and we'll click confirm and have CalcBook load that up for us. So here's our typical CalcBook layout, right? On the left side here, we've got all of our inputs. So we start going through our checklist. First thing we want to do is decide if we want to include our wall weight. We're going to leave this as yes, because the problem statement said that the applied loading did not include the self weight. Foundation check, right? You can select this. It will evaluate the foundation for overturning and sliding and that sort of thing. But we're going to go into detail on foundation design in another video. So for this calculation, we're going to ignore this so that we can just focus on the shear wall design. So we start entering our wall dimensions, right? We've got an 18-foot long wall. It's 12 feet tall, and it's got a thickness of 10 inches. We've got our vertical reinforcement of, let's see, two layers of number fives at 18 inches. Our clear cover on each end, right? We can leave that at 1.5. For our horizontal reinforcement, that's also two layers. It's number fours, and that's going to be at 16 inches. And we've got some other items which we're not going to change the soil, right? We're not doing that, so we're not going to be looking at bearing pressures. Our material properties, right? Normal weight, leave that as is. 4,000 psi, 150 PCF, 29,000 KSI for modulus elasticity, and then our yield strength for the steel reinforcement at 60,000 PSI. So we're good there. Then we can go over and enter in our demands, right? We are going to use the ASCE load combinations. So for our flexure demand, right, we've got a wind moment of 4,670 kip feet. Our axial demand dead load is 230 kip. Our live load is 115 kip. And our shear demand for wind is going to be 121 kips. Now, before we go into the detailed calculation, right, we can already see here in our quick output window that we have a DC ratio of 0.95, which is controlled by flexure. But now we can go into the calculation and take a look at those details. So first thing is determining all of our demands, right? We have our supplemental loading, so that's going to be the weight of the wall. So it's going to be our applied dead load plus the weight of the wall is going to equal our total dead load, right? Then we've got our various load combinations, our various controlling load combinations for each loading direction. So our flexural, axial, and shear demands. And then for bearing pressure, this is not going to show anything because we've selected no, but if we had entered to evaluate the bearing or the foundation design, it would include the demands for that here. So now we can get into the calculations. So first we want to check our reinforcement ratios, right? For horizontal reinforcement, we've got a reinforcement ratio of 0.0025, which just meets the minimum requirements. We check our max horizontal bar spacing, which is the minimum of these three items. And we come out with a maximum of 18 inches, and our bar spacing is 16, so we're good there. Then we go and check our vertical reinforcement. We've got a vertical reinforcement ratio of 0.0034, which just meets our minimum requirement. And then our maximum vertical bar spacing is 18 inches, and we barely meet that as well with our bars spaced at 18 inches. So next we want to go and check our flexural capacity, right? So first thing we need to do is determine if we're a tension or compression controlled section, right? That gets us our beta 1 value. And then we need to determine our strain diagrams, right? Our strain diagram values. So we have a couple factors here, and then we can figure out where our neutral axis is. We calculate our depth to the extreme tensile fiber. We have our strain of concrete, our strain of steel, and then we can calculate our phi factor, which is based on the tension-controlled section, which is going to be 0.9. And then from that, right, using equilibrium, we can determine what our moment capacity is using this diagram here, right, with our axial load, our moment, our tension in the steel, and our compression in the concrete. So using that, right, we get a nominal moment of about 5,500 kip feet. And when we have a design flexural strength, including our phi factor, of 4,922 kip feet. Then we can go check our shear capacity, right? First thing we want to do is check our wall ratio, right? Which gives us our alpha factor, gets our phi factor, and then we can determine our shear capacity. And this is something that's changed in the 2019 code ACI 31819. Now includes the steel capacity in one equation. Previously, it was a separate equation for concrete strength and steel strength, and now this is all wrapped up into one equation. So we find that our design in-plane shear strength is about 550 kips. And then we also check axial, right? This is not going to control for this design because we have a pretty large moment and shear. But in some cases where maybe you have a very low moment, a very high vertical or gravity load, you want to just check this as well. So we do offer this calculation as part of this design module. So that is shear wall design in CalcBook. We hope you enjoyed this video and stay tuned for the next one.